Okay, welcome back. Before I forget, I want to make one remark. I looked at your, oh, and some of you actually did not submit the written sheets. You can do it after class, that's fine. Just make sure your names are on them. Uh, this was very well done, actually, from what I saw. The only remark I have is you must differentiate between a count, which is a whole number, and a proportion, which is a, what's the word I want? A proportion is a fraction, that's right. They are related, yes, but a count is a whole number and a proportion is a fraction. Now, these things may not seem like a big deal to you, but they are a very big deal in math, and we have to keep these things separate. All right, good. Also, two remarks that I forgot to mention on day one of the syllabus discussion. Um, if you come for office hours, and I strongly encourage you to, you will find most often my door is shut. So don't feel that, oh, that means I'm not taking office hours. That's not the case at all. I shut the door because my office is at a very busy intersection, not on the road, okay, but in the building. And so it gets really noisy with a lot of people walking around, talking and all that. So just knock on the door. I will let you in, of course. All right. So just knock on the door. Don't feel like you're disturbing me or anything like that. The door closed is not because I'm not having office hours. All right. Just letting you know. I keep forgetting to say this, and then I don't want people to. Okay. The other thing is this: some of you may not be aware. The homework, and I'm very gratified that so many of you have started that homework zero. You should, if you have not. Homework, you have unlimited attempts. Technically, it's 100, but because I have to put a finite number, but it's more than enough. So if you are not happy with your score, which you can see on Moodle, you can go to another attempt. All right. So just getting these two things out of the way. Now, here's what I want to do first. I'm going to discuss another written sheet today. We're going to do quite a few of these. I publish written sheets on Moodle after we are done with them. So that's why written sheet 0 is already on Moodle. You'll find it there. Now, we're going to do written sheet 1. There are 4 pages to this one. We will discuss page 1 together on Scratchpad first. All right, because I want to introduce the ideas before we do it on paper. So I will start you off with this and write down the outcomes that you might see in a physical population of voters. So let's say voters have to choose between two candidates, X and Y, and let the letters represent who you choose. So you might see something like this, okay? Do you agree? These are people, some choose X, some choose Y. So can I now ask you to contribute? Write down the outcomes you might see. If I took a random sample now of 20 voters, can someone do that? All right. You don't have to copy mine. Actually, I'm hoping you don't. Can you do what I just did? But if I randomly sample, now I'm putting dot, 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 dot here. And you know why? If it's a population, there's far more people than this. I'm not going to waste any more time listing out any, but you get the idea. Now, for a sample, should you have a dot, 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 dot? No. How many people should I see? 20. So can someone do that? Right? What will you see if I took a random sample of 20 people and asked them, who do you choose, X or Y? This is not a trick question. Can someone do this? All right. So if you pick 20 people, so there shouldn't be a dot, 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 dot. There should be 20 letters as your answer. There's no right or wrong answer here because it's what you might see. Yeah, something like that. Just make sure there's 20 of them. Now, would it be wrong? Would it be wrong if you wrote all X or all Y? No, it's not wrong. Good. Okay. So get these ideas in your head first. All right. Now, write down the outcomes you might see in a process population. Now, what do I mean by a physical population and a process population? I'm trying to sneak these things in without formally telling you what they are. So I'll tell you what they are now. A physical population is what it says. It's actual people. A process population is a population, but it's abstract. And the word process tells you that it's something that you don't observe tangibly as a thing, but that doesn't stop it from being a population. So What do I mean by a process population of free throws? If I kept doing free throws, don't I generate a population already of free throws? But the free throws are not physical things. But that doesn't stop it from being a population, right? I call those kinds of populations process populations. Because it's not a thing. You can't touch a free throw, but yet it behaves like a population. So if I did free throws, what might I see? So again, I'm going to represent this. I don't know what symbol should I use? If I make the, okay, let's say B and N. B is basket, N is not, or something like that. So basket, basket, not, not B and B and B and B. You get the idea? Again, this is a population. Should I have a dot, 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 dot like that? Yes, because a population actually has millions, potentially billions of members. Now, can someone write down the outcomes you might see in a random sample of size 20 of free throws? Use the same symbol that I've introduced, okay? B and M. What might I see if I took a sample of 20 free throws? Yes, good. There should not be a dot, dot, dot. It should finish. The sequence has to end. But do you realize you don't actually know how many of them should be, how many should be N? That's the subject for another worksheet, which I'm going to give out now. So very good. This is well done. That's it. This is the first part. I want to do another one. And in this one, I want you all to think about what physical population you would like. And I leave that blank. It doesn't have to be voters or elections or anything, but it should reflect some kind of a yes or no response. All right. So see if you can come up with something. If you cannot come up with something, then just use voters. That's fine. But try to come up with something like a voting situation where there are two outcomes and you have to choose one. All right.
It's okay. No, you're good. I feel like a pack was supposed to voters, but like a
Oh,
population
okay. Every group is kind of full. Do you mind working on this? I think this. Oh, no. I think all 28 are here.
Trying to figure out so it can't be
Yeah.
it can't be a number. It has to be a category.
Do you want to do this or do you want to work on it? It's fine.
Yeah.
And it would appear like
So what do I mean by this?
Could do that. It could be
Write down the outcomes you might see in a physical population of, well, think of something other than voters. See if you can dream of something else. But it has to be a real thing, physical. All right? And then do the same thing, but for a process. Try not to do free throws, think of something else.
Yeah. Or like short things. But what's like, what do they choose? I have to go back to the shop. But that kind of varies, not everyone. It's not.
Right. Exactly.
It's like something they're choosing.
Well, it's not a choosing. Yeah. The grocery shoppers, they buy apples.
Yeah.
Oh, that's good. That's good.
Apples or no, right?
What?
What's the criteria? So you're looking at people's shopping carts, whether they bought apples or
Or would it be organic or not organic of the same fruit?
Oh, yeah. For that.
yes. So, but you have to restrict it to people who buy fruit at all.
Oh, so
Because not everyone,
buyers.
but yeah. So among those who bought fruits, yeah, that's fine. You can. But yet, because it has to be a yes or a no, you don't want a third category of people who didn't buy fruit, and then so we're not going there. But yes. So among those that did buy fruit, organic or not, yes.
Okay.
Good. Okay, if you're done, you're happy with what you have, just give it back to me. It shouldn't take you that long. It's very hard to get this wrong, actually. I just want you to dream up a situation for a process and a physical, and just put your answers here. But I want to see so that I can talk about it, actually. All right?
Oh, yes, students. Sorry, I'm writing. I'm just clarifying what we're talking about. Like,
Okay.
the buyers. Yeah. Oh. Oh. Okay. Like,
Yeah, that's simple enough.
okay.
I don't think it's
Oh, I realize there's two sides to this because there's a continuation, there's a page 4. So hold on to your papers. I'll just have you give me some examples on spreadsheet, okay? So
On the other side. This is the one.
So here's what we will do. So this is page 2. Write down the outcomes you might see in a physical population of. Okay, write down some of your ideas here. Don't write down the outcomes, just give me the populations that you dreamt up, right? And please detail what about the population are you measuring, all right? Okay, remember that you must try to replicate what I did. You're not actually counting anything. You are basically sampling the population and asking them a yes or no question or choosing between two things. So align your answers along those lines, all right? There's nothing wrong with having a population of workers, but what are you asking them and what responses are you collecting? That's actually very important. All right? Yikes. So ugly. Do you support X or Y? And then this one, process population, basket or no? Ah, very good. This would work. Do you prefer dogs or cats? And you have to choose one. You cannot say fish or something. Okay. Okay, good. I want it to be binary. Good. The people with blonde or brown hair. You know what? Let's be very math about it. Can you say blonde or non-blonde hair? Because if you say blonde or brown, it's going to be hard because there are people who really don't have either one. So let's say blonde or although I don't think anyone has ever said non-blonde, honestly. That is so math, okay? I have non-blonde hair, right? Okay, okay. But yeah, I'm glad this happened. I want you to give me binary things, basically. Good. See, do you prefer dogs or cats? Do you work on weekends? Yeah, good. See, okay. Can I have some samples of what you might see? So for example, the weekend one, why don't you use W for yes, I work on the weekends, and N for no, I don't, something like that. And then the non-blonde and blonde, you can say B and N as well. Non-blonde is an N. You know, you get the idea. Dogs or cats is easy, B or C. So can I see some samples of that? Good. And I think that's very good. So the idea is, when I say population, yes, I want an unlimited string of things, but I want binary responses from the population. But you are actually talking to people, the physical population. Now, I'm very interested now to see, do you know the one about the process? And I think we will just skip the one about a sample. You know that a sample is limited in number, and that kind of, so no dot 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 for a sample. Good. Now, what can you think of for an abstract? This is a little bit more challenging, and I'm very interested to see what ideas did you come up with, right? What are some processes that behave like a physical population? It's just it's not a physical thing, right? Okay, test score. Did you get an A? Okay, so very good. But I wouldn't say A or B because what are people going to see? So what am I going to say? You get an A or a non-A. That's right. Did you get A or not? Okay, make it binary, but this is very good. This is a very good uh, example of a process population. Because a result on a test is a trial, it's not an actual thing. Very good. Right? Anyone else come up with anything? I'm actually very interested. I have some other ideas that you will see actually on page 4, but don't turn it over yet if you can. Yeah, did you get an A or not? Good. Anyone else come up with any other processes? And can I see a sample of a sequence? Again, you can use A for A, and non-A you can put N, I guess. Right? You did not get an A. Correct. Yes. Look at the temperature below freezing, or get the daily temperature, if you like. So that every letter represents the daily temperature of a day. Very good. Yeah. Uh, what is the game? Yeah, I don't play games on the computer at all. Okay? So I have no idea what this is. I vaguely, right? So yeah, yes. Did you get a win? You can say loss, okay? When you can use an English word, please do that, okay? A non-win is a loss. Unless you can draw. Can you draw in Fortnite? I don't know, right? If you cannot, then you can say loss, okay? Good. So you're getting the idea. Did we have a below freezing day or not? And right now, most of them will be below freezing, right? I don't think even the maximum is going above freezing, right? Which is horrendous. Okay. Okay. So so we good. So now hold on to your sheet of paper. This is idea solve. The key thing, a few key things, very important. Populations come in two kinds. There are physical ones and there are process ones. Process are slightly harder to process because they're not physical things, but they're not that difficult to understand. Both have binary responses. Remember that, right? And a sample has to stop somewhere because a sample, by virtue of the fact that it's a sample, has a size. So, but a population actually in mathematical theory goes on forever. And so we use that powerful symbol dot dot dot. And in math, dot 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 is extremely powerful. Okay, it means it goes on forever. Okay, so let's do side 3. And side 3 is a slight variation on this, where I want you to think a little bit more about the population if I tell you something. So let me get that one, okay? Where is my, oh yeah, okay. So written sheet, yeah, okay. So okay, side 3 looks like this. Okay, so let me copy these first. Okay, let me put this on Scratchpad and we'll work on it together. Year 4, this is 3. So as usual, 4 is I want you to come up with ideas of your own. So write down your outcomes you might see in a physical population of voters, again, I want the population side first. If you knew, look at the if you knew, this is new. There's some new information here. If you somehow know that the population, in the population, 30% support X, can you give me a string of letters that would represent knowing that information? What do you think your population looks like? Give me a string of X and Y's that kind of respects the fact that I have told you 30% support candidate X in the population. Right? What do I want to see? Yes, I want to see, I want to see more N's than X's, correct? But does it exactly have to be 30%? No, because a population in theory never ends. And so what should you do? You put a dot. But this means this is something you might see if you knew something about the population. See, previously I didn't tell you anything. So you just put X, Y, X, Y, X, Y. Okay, but if I tell you a little bit more about the population, then you know that your sequence should not be unreasonably too many X's inside, because only 30% support X. Okay. Now, look at this question. Let's say we now have a random sample of size 20 and do this for a sample that you are likely to obtain. I'll make this a little bit clearer. If you knew that 30% of the population supported X. What do I mean by this? If you know that you are taking 20 people from a population in which 30% support X, and I take 20 people from there, that's not the population. I'm sampling 20 people from a population where I know 30% support X. Can you give me the technical word is realization, all right? One sampling of 20 people from a population like that. Can I have an answer like that? That's likely to be seen. Right? Now, I like the fact that this answer has exactly 6 X's and exactly 14. It's not wrong. Is this quite likely if you know that your population is 30% supporting it? Yes. But can someone suggest another one that wouldn't be wrong either, that would be likely to be seen if you take 20 people from a population where around 30, no, not around, where you, in the population, 30% support X. Can you give me another example of a sequence of 20 letters which would be likely to be seen in this scenario? I mean, it doesn't have to be this. Can you give me another one that's different from this, that also respects the fact that it came from a population where 30% support X? And I think you know where we're going with this. Maybe let's do something extreme. Can you give me an example of a sample of size 20 which came from a population where you know 30% support X, but this kind of sample is not likely to be seen? Not impossible, but pretty unlikely if you know that 30% of the population support X. Do you know what I'm saying? Maybe don't answer this one anymore. Let's look at this one. If I tell you that in the population, 30% support X, now I go out and collect 20 people. That's not the population, I collect 20 people. Can you give me a sample that is quite unlikely to be seen, not impossible, if you knew that the population is 30% supporting X? All right? If someone knows what I'm saying, just give me an answer and we'll talk about it. I want 20 letters. It represents a sample of 20 people that came from a population that 30% support X. But this is a sample that's pretty rare to obtain if that were the case. Okay, so you can see here, see how many X's are there? I think it's 10, right? I think, okay, that's 10. That means in this sample, how many percent support X? 50%. Is this something that can happen when you sample 20 people? Now, the answer is actually yes. If you take a population where 30% support X, is it possible that your sample has 50% supporting X? It is. It is. This is part of what actually goes wrong with polling because sample sizes, even though polling has thousands, it can be inaccurate sometimes. This is like, can someone give me an even more extreme sample that can be seen? It's not impossible. I'm saying it's not likely, not to say impossible. Okay? Yes, good. Can this happen? Yes. Is it likely to happen if you knew the population is 30% supporting us? Not likely. That's exactly what. So, can you now answer this one? Can you give me another realization now that's likely to be seen if it came from a population with 30% support X? See, this one has 6 X's and 14 N's, which is fine. But can you give me something like this uh, as well that might be seen? That's also quite likely. See, they've been doing the unlikely stuff. Can you now give me something likely? Good. Yes, this is what. Is this exactly 30% of the sample? It's not, because now there's five X's, which means this is 25% supporting X. That's not 30%. Is it wrong? No, it's not. These are things you might see if you sample from a population with 30% support X. Is my point coming through slowly? Today's class is, I would say, the most important in the entire semester. So you're really going to have to really pay close attention because these ideas are not difficult, but they might be new. I don't think you've ever been in a statistics class where it's taught exactly this way. Most professors and teachers throw a bunch of formulas at you, but we are trying to help you think about statistics from a very, very foundational level. And that's why I'm not even giving you any numbers yet. Okay? So these are samples that are quite likely if you knew 30% supported X. Let's just ask you for one more. Can you give me one more sample that you might see as quite likely if 30% support X? Still with the likely, all right? Good, yes. So something like that. So do you see what you're doing? You're giving me this one has 6, this one has 5, and now this one has how many X's? And this one has 4. Yes, that's okay. You know what I think would not qualify as likely? Things like this, where you have 10 X's already. That's quite high. Not impossible, but it's already 50% support. That's quite distant from 30% already in the sample. This one's 100% support X is super extreme, not impossible. And no one did this, but this would be okay as well. This is also very extreme. If I have a sequence of all Y's, it could happen. But if you knew that the population is 30% supporting X, this is highly unlikely to happen, not impossible. Highly unlikely. Okay. So, you know what? I would like you now to just do this on Scratchpad. I don't need you to dream up a situation. Now, this is a physical population. I believe I have an example now of, yeah, we might skip 4 because I think I don't want to do overkill, and I think you all are getting the idea. So let's do 4, where I do suggest a process population. Oh, okay, no, this one. This one's quite good. Okay, I'm purposely giving you now a process population. And I want you to think carefully about this. Write down the outcomes you might see in a process population of free throws if you knew that 70% is the long run success rate for free throws. So give me a sequence of B's and N's. B is for basket, N is not. If I tell you that my free throw rate in the long run is 70%. Can you give me a sequence of B's and N's that respects that information? All right. See, I'm telling you that when I throw free throw in the long run, billions of times, 70% of the time I get a basket. Can you give me a sequence like that? What should you have more of, B's or N's? B's, correct? So any sequence like that will be fine. And good, you put a dot, dot, dot in, very good. Now, I'm going to sample 20 free throws. Do this for a sample which you are likely to obtain if you knew that 70% is your rate, free throw rate, right? Right? Do you see what I'm getting at here? Can you give me now no more dot, dot, dot. Can you give me 20 letters from a sample that you are likely to see if you knew that my long run free throw rate is really 70%? Yeah, something like that. As long as your B's are about 70%, that's quite likely. All right. I didn't bother to count, but I'm guessing it is correct. I think I see 14 and 6. Yeah. Okay. All right. Good. Again, does it have to be 14, 6? Does anyone dare to give me something else that's likely as well? This is important. What I'm trying to say is, when you sample from a population of free throws where the long run throw rate is 70%, do I always get samples of 70%? No, I don't. So can you give me another example? Good. I see a lot of B's. And yes, he added one. Yes, you can. Okay. The moral of the story is any observed fraction that's kind of close to 70% is likely to see. That's what I'm trying to get across to the class. If the true rate is 70%, you would expect most of your samples that you do to be close to 70, not exactly 70% all the time, but close to. So, can you give me unlikely samples of size 20 if you knew that the true free throw rate is 70%? All right. Can you give me some which are unlikely to be seen if somehow I know my long run free throw rate is 70%? See, now I'm not making the basket many times, certainly not 70%. Good. And this one stops at 20. So you see, this is the reverse. I think this is a 6 on this is a free throw rate of in according. Okay, can someone tell me what is the free throw rate in this sample? In this sample, 30%. It's 30% distant from 70%. Very good. This is very unlikely. Can you give me something that's even more unlikely? That does not respect my free throw long run rate of 70%. Yeah, right. Really having an off day, so nothing. It all ends. Good. Again, let me stress, these things are, and this is also unlikely. That's right. Anything that results in a rate in the sample that is distant from the population rate is unlikely. Not impossible. It's not impossible, but unlikely. Okay, so armed with all this information, I now want us to do something. I'm doing this for the first time. We'll see if it works out. Okay. I found this website literally half an hour ago, and it works well. You can find anything online. Honestly, okay. And so I found anything. So I found this. It's an online coin tosser, right? And I want us to do this together. Here's what okay, I'll show you how it works. Okay, first of all. Now, the person that made this, there's a little bit too much that you do. There are things we don't need. There are things we don't need. I'll demonstrate how this works. So we've been just talking about free throws. Let's just go with that. Right? Let's extend that example. Do you know that you didn't have to dream up this sequence? You could actually have been pretty lazy and got this to generate. I'll show you how. Now, I told you, I'm taking a sample of how many throws? I think we went to 20 all the time. So if I went to 20 tosses, and let's simplify things. Okay, just pick one row. I'll explain what that is in a minute. Do you see there's a prop head? All right. I'm going to change this from 0.5 to, can you guess what I'm going to change it to? 0.7, why?
7%.
Didn't I proclaim that to be my free throw rate in the long run? So what am I doing here? I'm saying I am making a coin that's weighted. The coin flip is replicating my free throw successes. I'm choosing 70% because that's my proclaimed long run free throw rate. Now, what happens? So if you hit this smiling face, right? What did it do? Did you see what happened? This is a sequence of how many free throws? 20. Do you agree that the T's and H's, okay, the T represents H is success. Okay, so heads are, you said you want heads 70% of the time. The heads now represent free throws that I successfully made. And is this a likely thing to see if you did have a free throw rate that is 70%? Notice, is this exactly 70%? I don't think it is. It might be, but I don't think it is. Now, here's what I want us to do. Okay, go to this page. You should find it on Moodle. I put it in the top section of our, it's an online coin tosser or something like that. I wonder if the website is going to crash. We'll see. Right? I want all of you to do exactly this. But here's what I want you to do. Just do 20 tosses. Make sure you put a 0.7. Do what I did. And just do one time, all right? One row. If this generates one, if you don't change, if you put 5, you get 5. We don't want that. That's not overtax the system. Just do one row, one simulation, 20 tosses at a 70% success rate. Now, here's what I want us to do. Compile your, it does tell you, doesn't it? It tells you I got 12 heads. See? So you can see, oh, there's, you don't even need to add it up. You can count it. So you see, you got 12 heads, that's 60%. That's quite likely. When you say that your long run rate is 70%, getting 60%, it can happen, right? It's not super unlikely. So I want us to put our answers. I don't know whether this is going to work. I'm going to try. We're going to use our data scratchpad for the first time. So I'm going to open this. Okay. I'm not, let me see. Can I? Oh, I can. Okay, that's too small. Okay, this is much better. Here's what I want us to do. I am going to ask you all to fill in these cells like that. When you run this simulation, sorry, tell me if you, okay, so 3, 4, 5. Okay, this is, okay, let me shrink these, okay, to something smaller. It's not very manageable right now. Okay, that's too small. So, Oh, okay, I see. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these last 3, I'll shrink them later. Now, here's what I want you to do. Run this simulation. Each of you just do one. There's 28 of you, so we'll get quite a lot. If that's not enough, we'll ask you to generate some more. Let's say, like me, you got 12 heads. Can you color this cell yellow? And so make it cumulative. So let me get what I'm trying to say. So let's pick a nice, okay, let's say green, all right? If you are someone that ran the simulation and got 12 heads, right? Make sure you put the prop head at 0.7 and do 20 tosses. If you got 12 like me, put another green cell on top of mine. So I want you to form a histogram, basically. All right. If you got 30, yeah, okay, good, right? Okay, do this. Everyone just do one. So there should be 28 colored cells being generated. We can extend this, so do this first. So the website is not hanging. That's great. Okay. Let me shrink this. This is really big. Oy. Very good. You do get what I'm saying. Do you see something happening? Are most of you getting a number of heads that's kind of close to 70%? Shouldn't that be the case? Didn't we ask the computer to generate what happens when I toss a weighted coin that's 70% likely to be heads? Shouldn't you be getting more heads than tails? Yep. Okay, so I think there's a whole bunch already. Can I ask you to do one more time? Because when we do things like this, it works really quickly. And actually, we can populate this. Maybe I'll ask you to do a third time, but let's just do one more batch, right? Do one more time, and you'll see something happen. I'm so glad I did this. Why are there some blue cells? Yeah, don't do that to me. I'm very OCD, okay? I really am. So because it makes it look like that's something exceptional or something like that. We might color some differently later for a purpose, but for now let's keep it all green. Okay, good. So is everyone doing one more time? Let's have you do it one more time. So we should end up with how many cells? 30, 30, 30. Oh, okay, 80, 80, 84. There should be 84, but I'm not going to count, but quite a lot. Do you see something happening? Okay, I want to do it until we see something happening that you recognize. Oh, yes. All right, very good. All right. See, isn't math wonderful? You are making a bell curve. Did you see that? And where is the bell centered? I'm a little bit concerned why there's so few here. Maybe there's something wrong with this website. Right? There should be a few more cases here, but maybe we have not run enough. See, we have only done less than 100. So maybe do one more time. Right? So I think we were told that students find it better when you do actual, but I think it takes too much time, honestly. I don't want you tossing a coin 20 times, 3 times, right? Using a computer is much easier, and this is something everyone can relate to and understand what's going on. So excellent. So you get a bell curve, and so the moral of the story is this: it doesn't mean that there's any particular number that you're near to. The number that you're near to is the proportion, well, it's a count, but it can be converted to a proportion. It is close to the proclaimed rate of success. So I'm going to ask you a question. I'm going to ask you to do it. If my free throw rate in the long run, all right, is 10%, all right, that may very well be the case. I've never actually checked, all right? Let's say it's 10%. What kind of graph would you see? Would you also see a bell curve? Where would that bell curve have its peak? Close to? If I really tell you my long run rate is 10%, and if I want to simulate what would happen, I would change the probability of heads to not 0.7, but 0.1. These green squares would kind of look the same, but they'll all be bunched up towards around how many percent? Where would they be? See, here, they're all kind of close to 70% because that's what you ordered. You ask the computer to tell me what happens when I toss a coin that's 70% heads. Well, most of the time you get close to 70% heads. Sometimes you get things that are quite low. Sometimes you get things that are quite high. That does happen. But most of the time they're pretty close to this. Pretty close to to where you say the process is centered. So you not answer my question. If I tell you that the process actually is about 10% only, where would most of the green squares be? Close to 10%. Okay, so these are very, very important ideas for you to understand. Now, I have, I think, a video that I think, should I? I think I can show you this if I can find it. Yeah, it's here. Okay. So I actually played with this in a at home. Right? So I don't know whether you can see. Okay, you know this is the name of this thing is a context actually. And you can see on YouTube there's a whole bunch of these. What am I doing? Do you see that I always in this and I check it. Yeah, I thought it was not that. If I could, most of the time, someone, oh, because I studied the and that's exactly what we generated using the computer just now. Okay, so with all this ramp up, we will now go to our notes and try to fill some of these things in. So let me get the notes that I want to talk. Okay, so you should have chapter 1 ready. So let's say I ask every person in the class whether they are left or right hand dominant. So I find that 4 out of 28 of you were left hand dominant. What would be the proportion of you that were left hand dominant? This is not a new question. This actually came out in chapter 0. Anyone give me a fraction? 4 out of 28. Good. All right. And this is a sample proportion because it came from this sample, which is this class. Okay. Now I know I'm asking something weird here. Is this number known after I've asked you this question? Yes, it is. It's not a trick, right? You do know the answer. It's 4 out of 28. All right. So this number is known after I have asked the class this question and collected the data from you guys. So here's a little bit of a symbol. And again, if you have done your written sheet 0, you have seen this symbol before. This is given the symbol p hat. YP proportion. The hat tells you it came from a sample from this class. Anything that comes from a sample is actually given an English letter. You'll see later, okay? We will introduce another symbol, but for now, just accept it. A sample proportion that you get to observe and know the value of is called p hat, right? A sample proportion. So p hat is 4 upon 28. Okay. A number that you get from the sample is called a statistic. And in English, it works out very well because sample starts with an S, statistic also starts with an S. So there's a lot of these alliteration kind of things to help you learn. And it works out really well in English. I'm not sure in other languages if it's so nice, but it somehow coincidentally works out very well in English. If a number came from a sample, right? I hope this class is not at the stage where you think that you're a population. You're not a population. All of hope is much bigger than this class. You are a sample. This class is a sample of hope. So this number, the left-handed proportion comes from a sample. It's called a statistic. So S with S, all right? The adjective sample is used here because information pertain to a sample, right? So numbers that come from a sample are called statistics. Now, are there other statistics I could get from you? Of course. I could ask you on how tall each of you is, and calculate the sample mean height, for example. That's another statistic. It came from a sample. So a statistic is not limited to just a proportion. There are other statistics as well. This is just one of them, all right? Okay. Would the proportion of current Hope students who are left-hand dominant be a number? You just say yes or no. Is the proportion of left-handers at all of Hope, is this a number? In fact, technically, is a proportion always a number? Yes, okay. It's so what else would it be? A proportion is a number. In fact, more than a number, it's always a what? It's always a fraction. Good. Okay. So the answer is, would the proportion of current Hope students who are left-handed be a number? The answer is yes. Now, here's a question. Is this number currently known or unknown to us based on information from just this class? Do we know the proportion of Hope students that are left-handed at this point in time? The answer is no, we don't. Good, we don't. Now, somehow, again, these are very basic facts. Something that's unknown doesn't stop it from being a number. Do you agree with that, what I just said? Just because I don't know something doesn't stop it from being the thing that it is. The proportion that are left-handed at home is not known to us. It's still a number. It didn't turn into a tree. It's a number, but you just don't know it. For example, what is the true population of Michigan? I don't think anyone knows the answer. It's a number, but we don't know. So numbers that you don't know pertain to a population. And we don't know it. Why? Because we don't have access to the whole population. It's still a number, but you don't know what it is. And so in this college, any number that pertains to the population that you do not know what it is given a Greek letter. So this is not p hat. What is p hat? Is p hat a proportion? Let's look at one slide before. Is p hat a proportion? It is. But what's different? What's the difference between p hat and pi? They are both proportions, but pi is the proportion that are left-handed where? Pi is the proportion left-handed among all of Hope. Is that a number? It is. Do we know it? We don't. That's why this is not p hat. You would be amazed that I've had many students, even at week 15, don't know what I'm saying. Cannot understand. Right? There are proportions that come from samples. There are proportions that come from populations. They are both numbers. One we are privileged to know, one we don't know. They are numbers. And because there are different statuses, we give them different symbols. That's it. Why is pi chosen? Because pi is the Greek P, in case you didn't know. Pi is the Greek P. And so they try to do this kind of, yeah, it's also a proportion, but we don't know it, so we give it a Greek symbol. It's a number, we don't know it. Okay? This is very, very, very important. P hat, things that you know are always given English symbols. You can see it, you can calculate it, you can give me an answer. But pi, you don't know. It's a number, okay? So I've dwelt on this quite a bit. Let's move on. A number that comes from a population that you don't know is called a parameter. Why did I say English is quite easy to learn statistics in? Because again, see, parameters are numbers, but they pertain to a population, P with P. What number pertains to a sample? We just did this one slide ago. A number that comes from a sample is called a statistic, S with S. A number that belongs to a population is called a parameter, P with P. It would have been a twist of cruel irony if it had P with S. That would just be wicked, right? But it didn't happen that way. Parameters come from populations. They are numbers, but we don't know what it is. All right. When you don't know something, can you hypothesize about it? Yes. So I could say things like this. What are some hypotheses you could make about anything? I can say 20% of Hope is left-handed in the long run, in the population. I could say 15% of Hope is left-handed. I could say less than 20% are left-handed. Do you understand what I'm saying? None of these statements are wrong or right. It is unknowable which one is correct. Why do I say that? Because until and unless you can interview everyone on Hope, it is not, you are not able to determine the veracity Whether this statement is true or not, whether this statement is true or not, whether this statement is true or not, you don't know. Now, that's the idea of a hypothesis. A hypothesis actually can never be proven to be true or not unless you access the whole population. Okay? So I've introduced a few things. I don't want you to freak out too much about this hypothesis, but a hypothesis is a statement about a population parameter. That's it. I'm going to ask you a funny question, right? Why do I not hypothesize about p hat? Because I'm right. Why would I say p hat is 70% when it isn't? That's stupid. But you will be surprised, and I think you know what I'm going to say. How many students on the exam write me a hypothesis about pi? They write p hat. You go, what on earth are you doing? Why are you hypothesizing about p hat? You can find out what p hat is. Don't hypothesize. You hypothesize about things that you don't know. Which is why I'm concerned, because I think fundamentally there's a disconnect. There are many students who do not understand the difference between p and pi. I mean, they know they have different symbols, but beyond that, they don't know what it means. So I'll say this again. P hat is the statistic that you get to calculate from your sample. It is given an English letter because it comes from things that you can see. Pi is no less of a number. It is a number, but you don't know what it is. That's why you hypothesize about it. Okay. Okay, free throws again. Let's say I asked you to do 55 free throws and you found that you made the shot in 47 of them. What is your observed sample free throw proportion? The word observed means you can calculate it. You can see it. Can someone give me the answer? What is my free throw rate in the sample? I made the shot in 47 of my 55 free throws. What is my proportion of making free throws in the sample? Is it a fraction?
Yes.
Yes. What is it?
47.
47 out of 55. Good. What symbol do I assign to this? Yes. Oh, yes. Not pi, please. Right? Because didn't I just tell you the answer? Right? You have the number in your hand. So it is p hat is 47 out of 55. Is this number known or unknown? Yeah, you better say known, right? It's there, all right? The number is known after you have done your hand. So because this is known, it's given a single p hat. Okay. If you did another set of 55 throws, what kind of score might you get? Can you give it? There is no wrong or right answer here. Do you know why? Did I tell you anything about the process? You don't know anything about your free throw rate. So any answer will do. Can you give me some answers? 30 out of 50, knock yourself on 0 out of 55, and 54, everything is valid. Or, except negative numbers and things more than one, all right? That doesn't work. So anything, anything, right? And this, I don't know whether you see, it's related to that sheet I gave out, you know? It's just talking about free throws now. Okay, would your long run proportion of successful free throws be a number? Is the long run free throw rate a number?
Yeah.
Yes. Okay, it is. But is this number known or unknown? Unknown, good. Why? Because can you ever actually finish doing free throws? Okay, you die. But what I mean is, while you're alive, potentially you could always do more. That's right. So the idea is that's the idea of a population. So is this so in other words, do you realize you never actually know your long run free throw rate? Because you can't finish doing free throws. So the answer is unknown. This number pertains to a population. And what is this population exactly? First of all, tell me, is it a physical population or a process? Very good. It is a process. What is the, well, it is the family or collection of all potential free throws you could do. So it's abstract. It's not a thing. It's a basket of tries. So this is the population here is a collection of all possible free throws you could make. All right. And because it is unknown, we give it a Greek symbol. Now, this is where a lot of things that you're used to can be a bit of a disservice. I am sure you have seen people say, like in baseball, what the statistics are. People tend to think of that as long run. You know why? They are saying, well, I've sampled so many tries of this person. I'm going to just treat it as if that's the population, but it technically isn't. You might close the thing and say that's the long run when the person, the athlete retires, maybe. But let's not get into all those details. The idea is, while you still can, it never ends. And so you actually never know what your free throw rate really is. Okay? Can you hypothesize about unknown things? Yes. Right? No one's going to stop you. So I could say, oh, my free throw rate is 0.72, I wish, right? Or 0.8. Most likely pi is 10.6. Right? But all these statements are valid about pi because they are just things you say about an unknown thing. Just like I said, I hypothesize that tomorrow it will not snow. No one's going to stop you from saying that. And you cannot know whether I'm going to be, you can only know tomorrow whether what I said is true or not. At this point, you actually cannot determine the veracity of my hypothesis. All right? Okay. So we have all these things. Okay. So now we'll go into something that we have also played with, typical and atypical scores. So let's say I somehow know, see, this is where this is called omniscience. Okay. Let's say I somehow know that the long run left-handed rate at home is 11%. Okay, this is the part that you have to imagine. Let's say in other words, what am I telling you here? Am I giving you the value of pi or p hat? I'm giving you the value of pi, yes. See? Let's say I somehow know that pi is 11%. The symbol for this would be, and you have just told me pi, not p hat, because it is the long run rate, not a sample rate. If you sampled 100 Hope students with the knowledge that 11% is the long run left-handed rate at Hope, can you give me some typical sample proportion? So the idea is this: Hope has about 3,000 students. I am telling you that 11% of Hope is left-handed in the population. Right? Don't ask me how I know. Right? Let's say somehow I know this. Can you give me now I go out and sample 100 Hope students. Can you give me some sample proportions left-handed that are typical if I know 11% of Hope is left-handed? Anyone? Just give me percentages. You don't have to give me, you can give me fractions if you like, but it's upon 100. How many people out of 100 that you sample from Hope would be typical to see if you knew that 11% of Hope is left-handed? This is very similar to what we just did of K3. Anyone? 11, yeah, on the nose, 11. What about, can you give me something else? 15? And anything close to 11 on either side would be fine. So these are typical things you might see if you knew that Hope was 11% left-handed in the long run. See, all these are correct. I mean, think about it. If you did this, if you went out and saw 100 Hope students tonight and you asked them, these are things you might very well see if Hope were 11% left-handed. All right. Can I ask? Each of this would be given the symbol what? They're all proportions. What symbol do we give them? Yes, because they came from a sample. Because is this all of Hope? No, these are samples. Or they came from samples. These are not samples, these are numbers. All right. They came from samples. Can you now give me some atypical proportions if I sampled 100 Hope students each time? Yeah, everyone left-handed? Or all right, basically anything that's really small or really big. Distant from 11% would be atypical if you somehow knew that Hope was 11% left-handed. Okay. Now let's get a little bit more. No one's ever going to do this, but let's say I sampled 1,000 Hope students. Why am I doing this? Well, if I sample 1,000, it's still a sample because Hope has more than 1,000 students. If I sample 1,000 Hope students, can you give me some typical proportions that you will see if you knew Hope is 11% left-handed in the long run? And you can tell me as a fraction if Actually, I'd rather you tell me, say, what upon 1,000? Yes. What's 100 out of 1,000? Isn't it 10%? Yes. Again, anything close to 11% is typical. We don't really care that it's now 1,000 students. The idea is the proportions that you see now should be quite close to 11%. And if you, I don't know, I've seen a lot of students in my time now, and can you easily convert these to percentage? I hope you can. Okay. These are all quite close to 11%, trust me, okay? Now, can you give me some atypical ones? Do you know, actually, if you're really lazy, you can actually cheat. Oh, it's not cheating, but it's actually working really smart. How would you make these atypical if I sample 100, 1,000 students? Anyone have any idea what I'm saying? What would you do to these examples here?
Multiply.
Multiply top and bottom by 10. Isn't 750 out of 1,000 kind of unlikely to see it? Yes. So in other words, there is a point I'm getting to, okay? See, so anything far from 11% is atypical. All right. Okay, here's an interesting one. Are you more likely, though, to get an atypical proportion if you sample 100 students or 1,000 students? Yes, it's more likely to be atypical if you sample. Why do people want large samples? Large samples will reflect the population more accurately. This is quite logical. If it were easy to get a good representation, people would sample like 5 people. We don't do that because there's a lot of variability when your sample is small. All right. So you are more likely to get an atypical proportion when you sample just 100 people. So the proportion that are left-handed in 100 sample students or the proportion that are left-handed in 1,000 samples, so which one is more variable? The samples that are of size? Sorry, which one's more variable? Sorry. In other words, if I sample 100 each time and I measured how many people are left-handed in 100, is there more variability in my answers when my samples are smaller? And the answer should be yes. Your samples are far more variable if your sample size is small. All right. Okay, so no, everything that has been written here are all possible to be seen. Nothing is impossible. But that's not what statistics is about. Statistics is not about declaring whether something is possible. Now, that's a pretty easy question. Anything you might see. But it's whether it is likely or not to be seen under a certain set of conditions. That's key. All right. Statistics is about quantifying the unlikeliness of what you just saw. All right. Okay, let's immediately, and we can run through this much more quickly. Let's say I somehow know that your long run successful free throw proportion is 78%. I purposely picked an ugly number, show you that it doesn't have to be nice numbers all the time. I have a 78% long run free throw rate. Again, don't ask me how I know this. What's the symbol for this long run proportion? Yes, good. Not p hat because it's long run. This one would be pi. Can you give me some typical scores out of 100 if I did 100 free throws, knowing that my success rate in the long run is 70%? Anyone? Any suggestions for me out of 100? Yes. 80, yes. 79, 78, 81. Anything close to 78% is typical. And I think you get the idea. So I'm okay. Atypical, anything far away from 78%. So anything too high or too low are atypical if you know that your true success rate is 78%. So if I attempted 10,000 free throws, still a sample because I could potentially do more. Can you give me some typical? What would you do to these answers? What's the easy way out? Just add some zeros to both the top and the bottom. Anything close to 78% would be typical. Anything far from 78% is atypical. And I think you get the idea. In fact, I think that's what I did for my note. Didn't I? Yes, I did exactly that. I dumped in a bunch of zeros to respect the fact that I took 10,000 tries. But you see, they are all close to 78% if it's typical, and they are all far from 78% if it's atypical. Right? Now, I would encourage you today, this class is extremely important. Go home immediately when you get back, review what you have just learned today and make it stick in your mind. Very, very important. All right? Are you more likely to get an atypical score if you did 100 free throws or 10,000? 100. There is more variability in smaller sample sizes. I think this is pretty logical. And so it is more, your scores will be more variable in samples that are smaller, right? Okay, and the key is to determine whether a score is unlikely or not. So assessing whether a score is typical or not. Okay, you know, I wonder whether the class is able to play with this one. Okay, so let's go back to the nice graph that we made. Okay, notice where are typical scores? Typical scores will always hang around the value that you made your coin head proportion be. So here I believe it was 70%. How would you know whether something is atypical? Well, looking at this, I would consider anything outlying around what we call the tail here is atypical. And not just here, the other side as well. Anything far away from the middle is atypical if you know the process rate. All right. So based on that, we are going to do, I think, one last thing. I think I can introduce this today. Let me go back to my notes. Let's say, okay. One way to assess whether an observed score is typical or not is to look at what happens when you simulate many times under a hypothesized value for the long run. What is this big word here? Okay. When we made that graph together, I hypothesized my true rate to be what? Can someone give me a fraction or a number of percentage? When we made that graph with all those green squares, what did I hypothesize the true rate to be that we made our coin adhere to? 70%. Very good. In other words, didn't we simulate many times under an assumed that that's what we did? That is exactly what we did. Okay. And so the second thing you do is observe the variability. And we have learned that there is more. Okay, let's talk about it less. There is less variability in your simulated values when your sample size is bigger. Not no variability, just less variable the larger your sample size is. Right? Oh, just look at the terrible side. Oh, I don't even know where I can find my car. I mean, I've been here a bunch of years. I still don't like it. Honestly. Don't like this. I don't know. Depending on where you're from, you might be used to this, or you may not. You know, if you came from the more southern part of this country, I'm sure this is kind of new to you. Right? I'm from Malaysia. Can you imagine? 3 degrees north. Right? So none of it. Right? We have rain like nobody's business, though. Right? Actually the thunderstorms that we have are as bad as the blizzard. You have like zero visibility. So actually driving in whiteout conditions is not something I've not done. Okay, I've actually done it, but with a different situation. But anyway, it's pretty bad. And I drove a small car and I could feel my car move, you know, aquaplaning kind of thing. It's pretty bad, actually. It's quite equivalent to this kind of snow hazard thing. Okay, why am I talking? Okay, so anyway, so okay, so I think let's finish by talking about this dolphin thing. We'll pick this up next week. Okay. So one way to talk about this is to give you what we call a pretty simple thing to think about. So there was an experiment that was done where between two dolphins, okay? They wanted to know whether the dolphins could communicate. All right. If we know they make sounds, we just want to know whether their sounds have any meaning. So what they did was one dolphin was put in one side of a tank, and this dolphin had to press one of two buttons, huge plastic things, I think. And so the dolphin on the other side had no buttons. So the dolphin had to tell the other dolphin which one to press. All right. There's only one choice of two buttons. One of them is correct. Now, the amazing thing is they tried this 16 times, and I think the score was like 15 correct. All right. That's pretty good. So the dolphin got it right 15 times out of 16. Now, so there's two buttons. So what am I going to say here? I want to know if there's any evidence that the dolphin really does know what it is doing. It's not just guessing. So let me just put the question in another way. In fact, let's not talk about dolphins. Let's talk about you. Right? Instead of a tank with two buttons, imagine you're taking a true-false test. That's your two big buttons. Right? And you did a true-false test with 16 questions. Right? And you get 15 correct. Is it possible to get a score like, I don't know, 15 correct out of 16 if you guess on a true-false test? Is it possible? Yes. Is it likely? No. So in other words, is 15 out of 16 an atypical score if you are guessing? Now, saying that you are guessing on a true-false test is the same as saying that my long run answer correct rate is how many percent? If I guess on a true false test, and it's important that you know it's a true false test, if I guess on a true false test all the time, what is my long run success rate? 50%. Good. So to know whether something is rare or not, we will go and appeal to this thing again. How would I modify this? All right. So I would need to generate how many tosses? Not 20, but 16. I would change this to a 16. And you know what? I'm going to do a lot of these. Let's see if we can do 100. Let's see. All right. I'm going to change my prop head now, not 0.7, but to what? 0.5. Why am I doing this? I want to know if I toss a coin 16 times, and the coin is fair, this is reflecting the true-false test. In fact, you tell me, if I toss a coin 16 times and the coin is fair, how many heads would I expect to get most of the time? 16 times. I toss the coin 16 times and it is a fair coin. How many heads should I be getting most of the time? 8. A typical score is 8 out of 16, 7 out of 16, 9 out of 16. What's an atypical score? 1 out of 16 or 15 out of 16. So let's see whether we are right. So let's see if this works, okay? Oh, it does work, and it takes its time, you know. So we have the time, that's okay. So we have some time to look and see. Do you see the results coming out? Most of the time, do you see that the heads are like 8, 7? Isn't that what we expected? Sometimes you get a lot of heads, 14. See? So is there a way to do this in a slightly less painful way? There is, and I will introduce this effort, right? I won't not ask you to do it, but I'll ask you to do it along with me. So if you go to our page, you will see there's something here called URL for applets. This one. So let me open this up. Because I've introduced, okay, go to one proportion. I'll do this again, don't worry. So do you see prop heads? You're going to leave them at 0.5. Do you see number of tosses? Not 5, but what do you think I'm going to do? I'm going to change it to 16 because I'm trying to replicate this true or false test, if you like, 16. And I'm going to not toss just one set. I'm going to do 1,000, which is what we didn't do in class. Do you see a bell curve form? Okay, so a few things to point out in our last minute together. Do you see that most of the time, when you use a coin that's 50% heads, 50% tails, you should be getting around 8 heads? Of course. So where was the dolphin's true score? 15, right? Where's 15? Isn't it way on the tails? Is it unlikely to get a score like 15 out of 16 if you're guessing? Yes. All right. Good. So with these thoughts in, try to review what you have done today. It's very, very, very important that you understand these things. Okay. So I'll see you all next week. All right?